Have you ever asked yourself, how is electricity made? To answer this question, watch this video. Hello everyone and welcome to this video where we will be introducing something called induction. So let's go straight forward into our topic. Just like a battery can store energy, a magnetic field can also store energy. So these magnetic lines or the magnetic field also has a form of energy inside it. This type of energy can be used to produce something called the electromotive force. And some of you may already heard of this term, electromotive force. It's another term for potential difference. There's, a small difference between them. It's not what we want to talk about right now, but it's just a form of potential difference or voltage, we could say. Now, we may be able to produce electricity using the energy that is stored inside a magnetic field. So we can produce energy from magnets. How is this done? So if it was found that if we move a magnet through a simple loop of wire connected to a voltmeter, the reading of the voltmeter will change. So this means that there must be EMF. EMF stands for electromotive force because electrons are now moving through the wire, so we are creating current. What caused the electrons to move through the wire? It was the magnet when it passed through a loop. Now, we call this induction. So moving a magnet through a loop to create electricity, this is called induction. Now, to understand what really happened, we must understand something that Faraday found out. Faraday found out that the electromotive force produced can be changed by changing the area of the loop. How is that? Now we're going to make it a little more simple and clear using a simulation. But we must understand a term he invented. It was called the flux. So if you are able to change the flux, you are able to make electricity. Again, if you are changing the flux, you are changing electricity. But what is flux? Flux is simply the amount of magnetic lines passing through the wire loop. So we said that if we pass a magnet through a loop of wire, we are making electricity. This is called flux. So if we are changing the amount of magnetic lines passing through a loop, we are creating flux. Okay, this is a little bit confusing, so let's just see this simple, very wonderful simulation prepared by PHET Colorado. They had made tons of simulations, wonderful simulations, so we will be using one of these simulations in our video. Let's look at this simulation. Here we have a magnet and we have a coil of wire, and the coil of wire is connected to a lamp. So let's start by trying to move this magnet through the loop of wire. We can see that we are producing energy inside the lamp, okay? Again, if I move it through the wire or the solenoid here, we are producing electricity. So what will happen if we switch this magnet? Will we still produce electricity? For sure, yes, we are still producing electricity. Is there a difference between using the magnet this way or this way? Yes, there's a difference, and we will talk about it right now. To make things more understandable, let's look at the field lines coming out of this magnet, okay? Now, remember the term that we called flux? Flux is the amount of magnetic lines passing through the wire. Now, for this instant right now, we have like, imagine 1, 2, 3, and 4 lines of magnetic field passing through the loop of wire. The lines are only an indication of the strength of the magnetic field. It doesn't actually mean that there are only 4 lines passing. It's just an indication about how many lines are passing. Now, as you can see, there is flux. There are magnetic fields passing through the wire, but they are not changing. For electricity to be produced, again, if you understand this, everything will become simple. For electricity to be produced, the flux must always be changing. So let's start moving the magnet. Now look here, the flux is starting to change. The amount of lines passing through the coil here are changing, so we are creating electricity. But the moment I stop, here, let's stop right here. For example, there is flux. As you can see, there are magnetic lines passing through the solenoid, but there is no electricity. Again, for electricity to be produced, the flux must be changing. So look here. Now, since the flux is changing, we are producing electricity. But at a certain moment right here, there are like, imagine 2 lines passing through the solenoid. So if I move it like this, actually the flux isn't changing because the amount of lines passing through the solenoids are not changing. So as you can see, there is no electricity production right now. But as soon as I pass it through the other side of the solenoid, look here, new lines at this moment right here, new lines are passing through the solenoid and we are producing electricity. Okay, since now we understand the term flux and that the flux must be changing to produce electricity, let's look at the effect of the poles used on the electricity. Well, actually, in both cases, we are producing electricity, either if the south side was close to the solenoid or if it was the north side. In both cases, we are producing electricity. But what's the difference between them? Let's look at this voltmeter. Let's add a simple voltmeter. Now, when we're getting the north side close to the magnet, we will have a certain direction of the current. Since the potential difference or the voltage is negative, that means that the electricity is going in a certain direction. See, if I move it to the left, it's going to the negative side. But look what happens as the south side is now closer to the solenoid. Look at the voltmeter. The voltmeter changed its direction. In other words, what's happening here is that we are changing the direction of the current. Again, look here. This time when the north pole is the closer to the solenoid, we are producing a negative, let's say a negative potential difference. That means the current is going in a certain direction. But if I do like this and I switch it to the other side and the south side is now closer to the solenoid, we are changing the current direction. So actually, if I do like this, if I'm going back and forth, back and forth, back and forth, what I'm doing here is I am producing an alternating current. And we must have heard about this term before. Alternating current is when the current is not going in one direction, it's going back and forth, back and forth. It's on the contrary, the direct current, the current is only going in one direction. But here we're not creating a direct current, we are creating an alternating current. Look here, let's switch the magnet, and the south side is now closer to the solenoid. We are producing a positive potential difference. Now, when it passes through, we are producing a negative potential difference. So we are just switching the direction of the current. Okay. Now, so first factor, the flux must be changing. Let's look at another factor that will affect the amount of electricity produced. It is the number of loops of the solenoid. Let's look at this solenoid right here. This one is made out of only 2 loops. Here we have approximately 4 loops. So the south pole is getting closer. We are producing electricity, but as you can see, the arrow here is not reaching the end of the potential difference or the voltmeter. The same goes for this direction. But let's look at it one more time here. We can see that the potential difference is higher in this case. So this means that we are producing more electricity. So the number of loops also affects the amount of electricity produced. Now, so we have the number of loops, the flux. Now, the third factor, you can say, it is the speed of the magnet passing through this wire. So let's move this magnet very slowly. We are producing a certain amount of electricity, and when it's leaving from the other side, it's still producing electricity as an alternating current. But look what happens to the reading of the voltmeter when I move it quickly. See, it's reaching the full potential of the voltmeter. The arrow is reaching to the bottom of the reading, or the high. It's giving a higher reading. But let's move it here fast. If we move it quickly here, we are still not reaching the end of the voltmeter. But here, if we move it quickly, we are reaching the end of the voltmeter. So, to sum up, the number of magnetic lines passing through a wire is called a flux. To produce electricity, the flux must be changing. How can we introduce more electricity or induce more electricity? By increasing the speed of the magnet or by using a larger number of loops. So all of these are factors to affect electricity. And it's common sense that if I use a bigger magnet, let's call it the fourth factor. If I'm using a bigger magnet, I will produce more electricity because I am introducing more magnetic lines passing through the wire. So I'm introducing more flux and I'm introducing more change in this flux. So I'm introducing more electricity. So finally, for one more time, the strength of the magnet affects the electricity, the number of wires or the number of loops in this solenoid or coil, and the speed of the magnet also affects the amount of electricity produced. I hope that made things simple. Sorry for taking much time, but I think it was worth it and it made things a lot simple. Thanks again for phet.colorado. I will put the link in the description of the video. See you next time.